Heat transfer example problem. Average surface temperature for cylinder in cross flow. An uninsulated steam pipe is used to transport high temperature steam from one building to another. The pipe has a diameter of 1/2 meter, which is pretty large. Air moves in cross flow over the pipe at a temperature of -10 degrees Celsius and a velocity of 5 meters per second, which is pretty cold and pretty fast. Please note that these conditions suggest the steam is being cooled intentionally for some kind of industrial application. However, high-quality steam such as this would typically be used to produce power. For this problem, find the average surface temperature of the pipe if the heat loss per unit length is 4,500 watts for every 1 meter section of pipe. Our first assumption for this problem is steady uniform free stream velocity and uniform free stream temperature for the flow over the cylinder in cross flow. This is a pretty significant assumption. Real-world flows will often not be that well aligned. Thus, we again acknowledge that the accuracy of our calculation using an ideal correlation is at best plus or minus 20%. Our second assumption is constant properties, which is reasonable as long as the properties have less than a 10% variation over the range of conditions. Our third assumption is that there is negligible radiation for the exterior boundary. This is a reasonable assumption for moderate temperatures combined with significant convection at the exterior boundary. Our fourth assumption is that the air is an ideal gas at atmospheric pressure, which will be used to look up properties. We begin our calculation for the average surface temperature by recalling Newton's law of cooling for total heat transfer by convection in terms of the average convection coefficient for the cylinder. Note that we will need to get a value for the convection coefficient from a correlation for average Nusselt number. Next, we solve for the average surface temperature, substituting in the known heat loss per unit length. Before continuing, note that the actual surface temperature will change significantly along the surface of the cylinder, and that the average Nusselt number correlations account for this variation. To begin the process of selecting a correlation, we note that most of the correlations we will use evaluate properties at the film temperature. However, since we are solving for surface temperature, we do not know this value ahead of time and will need to assume a reasonable value and then iterate until convergence. For the steam in the pipe, if we assume it is above the boiling point at atmospheric pressure, a reasonable guess is 350 Kelvin. The properties for air as an ideal gas at atmospheric pressure are as shown. Next, we calculate a Reynolds number to help determine the flow regime, which is generally needed to select a correlation. We then refer to our textbook to find a correlation for average Nusselt number for a cylinder in cross flow, and note that we have 3 options that are valid for our flow conditions. For this example, we will use the simplest one. Note the different Reynolds number ranges correspond to significantly different flow regime ranges. At the lowest Reynolds number range, the flow will move very slowly over the cylinder in laminar flow with a steady recirculation zone behind the cylinder. At the highest Reynolds number, there will be a laminar boundary layer on the front half of the cylinder that will separate at the top and bottom of the cylinder, creating a wide turbulent wake behind the cylinder. Our Reynolds number corresponds to this latter case, and we select the appropriate values for the constants C and M. Substituting in values, we get a Nusselt number of about 300, a convection coefficient of 17 watts per meter squared Kelvin, and an average surface temperature of 154 degrees Celsius. Finally, we check our assumed value of film temperature and get an updated film temperature of 345 Kelvin, which is only about 5 degrees lower than our original guess. Thus, when we look up properties at this temperature and repeat the calculations, our answer for the average surface temperature changes by less than 1%, and we can consider our solution converged. On a final note, I recommend that you use EASE to solve problems that require iterating for property values because it has property databases available that automate this process.